5.6, Section 7.2, circular motion, Section 7.3, gravitational force. Okay, that conceptual example we just went over, obviously, is something good to have. It's not going to be in the recording, so if you listen later, you're not going to hear it. You want to do an example of each? You want to talk about each first? What do you want to do? Example of each of them? Is that a good way to approach? So something in circular motion, we have two formulas. Okay, those are the two. Now, remember, you're not going to be given the second formula there because you don't need to be given it. Remember Newton's laws. If that's Newton's law right there, and you want to find centripetal force, you don't use regular acceleration, but you use centripetal acceleration. So technically speaking, you're just going to take this, remember, and plug it in right there for acceleration. That's where this bottom formula comes about. M and times acceleration. These are the same things. Okay? So again, just to remind you that the force that you're going to find does not necessarily need to be memorized, does not necessarily be given, and you don't have to memorize it either. All you need to know is that if you use the acceleration and F equals ma together, you get that every time. Some people came in this morning for office hours, and we went over an example, and one of the things I said, which I want to mention, is that if you find the acceleration in part A of a problem, give me a number that's greater than 10. Pick a number. 11. If you find the acceleration to be 11, you can simply plug the acceleration in to this formula right here. Plug in the 11, and then multiply by the mass, and you'll get the centripetal force. You don't need to redo the problem again. So again, if you find the acceleration in this part, you don't need to then go ahead and plug in V again, R and M, and find the force. Just take whatever you get for the acceleration, take it here, and multiply it by the mass, and you'll get the force. Or you can use this formula. It doesn't matter, but I'm just trying to save you some time. Okay? So let's say we have a car going on a track, and the radius of curvature is like 15 meters. We also know that the velocity of the car tangentially around the track is 35 meters per second. Let's find three things. Let's find the centripetal acceleration. Let's find the amount of G forces acting on an object. And let's find the centripetal force. Okay, with these values here. How would you find the centripetal acceleration? What would you use for that? Maria? Good. What do you get from that? Somebody give me a number real quick. It's 81.6 repeating? Yeah. Now, is that a big or a small acceleration? Is that a big or a small acceleration? Big. Why big? Why are you saying big? Because it's what?
Isn't it like 80 miles an hour?
Well, that's an acceleration, not a velocity. It says it's a big acceleration. The velocity we can convert to miles per hour. We can't convert that there. Why would you say it's a big acceleration? The answer is it's pretty big. Why is it big? Relatively speaking, obviously.
Because the radius is pretty small.
Yeah, the radius is really small and the velocity is pretty big, right? That's why it comes out to be a big number. But how can I tell? What is that much bigger than? What number do we know?
Gravity.
Yeah, gravity on Earth. What's gravity on Earth? Yeah, that's almost 10 times that, isn't it? It's about 8 times that, really. So for part B, we're looking for the G-forces. That's what we're going to do. We're going to take that number divided by 9.81. God bless you. To see how much bigger it is. How much of a factor greater it is. So take 81.6, please. Go ahead and divide it by 9.81. What do you get for that, Joyce?
8.32.
So there are 8.3 G-forces acting on this person. What does that mean? What does that mean? What does it mean for, God bless you, a person to experience 8.3 G forces?
Isn't that like the G force is pushing down someone? Like they're adding weight to them?
Yeah, so Smitty, you don't normally feel like, you don't feel just your normal weight, you feel your normal weight, but in addition to that, you feel what?
You're going to feel the G. You'll eat food, your gravity.
Yeah, but how much more than that is the question? What does that 8.3 signify?
That's 8 times gravity, so 8 times 9.81.
Yeah, so normally you would feel your weight, right, when you're sitting still? That's what you feel. If you were traveling in this car at that velocity with that radius of the track, you would feel 8 times your weight when you're feeling that centripetal force acting on your body. So when you're in your car and you feel your body like flying out toward the car and it pushes back, well, your car is to push back with a force 8 times that of your weight. It's a large force. It's a really large force. Can somebody quickly go to Google and convert 35 meters per second to miles per hour? Just type in 35 m/s and the word 2 and then mph. Race has it, it looks like.
Uh, 78.292.
Yeah. 15 meters, that's 45-foot radius. That's a pretty actually sharp turn on a highway. Imagine taking a sharp turn at 80 miles an hour. What do you think would happen to your car?
Flip.
Probably flip. The centripetal force, we're going to calculate in a moment in part C, would most likely exceed the force of friction that's allowable between the tires and the road. Let's go ahead and calculate FC. Either use the formula mv squared over r, or take the acceleration you got and just multiply by, whoops, we need a mass. The mass of the car, which happens to be 1,000 kilograms. Multiply your acceleration by that. You can just move the decimal over 3 spots. And you get your answer nice and quick. Take the acceleration, 81.6 repeating, multiply by 1,000, that'll give you the force. You don't need to go through the whole formula if you have the acceleration already. If you didn't have the acceleration, then you could plug it into mv squared over r, that's fine. What do you get? 81.6 repeating times 1,000? And use your brain, a little more than your calculator. Yeah, 81,600. Or 81,666 if you kept those decimals from the last part. Okay? So 81,000 newtons of force. So there's a good chance that a problem like this, your car is not going to be able to resist the centripetal force that it's going to need. So what's going to happen is you're going to have some slippage in the tires in the road. The back tires will fishtail out and you'll start to slide off the road. The whole car will slide off the road at this point.
Are we going to need to know how to find G forces on the test?
Absolutely. It's really simple. You take whatever your acceleration is and divide it by 9.81. And that's what it is. Always. Because remember, G-forces is really a ratio of the acceleration you feel to Earth's acceleration. It's a ratio of the acceleration you feel to Earth's acceleration. The reason I say yes to that, Phil, is because you hear the term G-forces all the time. With people on like rocket ships, with cars. So why not know what it really is, right? I think it's useful. It's a good application.
I read about proposing space stations. They're always rotating to like create their own.
Gravitational field?
Yeah, is that similar to this?
That's exactly right. Back to Ender's Game again. I gotta say it, it's true. In the first book of Ender's Game, they're in space, and what do? They create a gravitational field by rotating at an exact velocity that creates an acceleration of 9.81. So they specifically rotate at a certain velocity, and they know the mass of the overall rotating object. They know what the radius of rotation is. At that point, though, you have to understand that different locations rotate in different ways. So it's a little bit more sci-fi there than what it really is. But the idea is that they're rotating to create acceleration of 9.81.
Wouldn't eventually people get nauseous because of the spinning?
I mean, realistically speaking, it's something that is not going to happen anytime soon because of the feeling you'd have in your body. Your body would not want to feel that all the time. Now, the other thing is that depending on where you are in the space station, you should be rotating at a different rate. Think about that. Because a different radius affects the force, right? So as the radius changes, if you're in the inner ring of the space station, and then the outer ring, and then the outer ring, they should technically be rotating at different velocities. So that would be just wild. Because how would you go between them then, right? So that's what the tough part about space stations and creating a gravitational pole would be. The idea is there. This is where the midterm ends, so up to this point, yeah. Okay?
Wait, I'm confused how to find FC. You just multiply 1,000 by 81 point.
Yeah, because remember, Mike, go back up to what I wrote about at the top. Look at the top up here, okay? Take a look up here. You could either use this formula, Mike. You could always use this, okay? If you remember, I'm circling it. You see it right here? Oh, you can't really see with the color. Hold on, let me change the pointer. Let's use the white hand. Can you see the white hand or no?
Yeah.
All right. So either use this formula. You can always plug in the mass, plug in the velocity, plug in the radius. What I did though, I said, well, we already calculated the acceleration, didn't we?
Yeah,
So I just used this one right here. Okay? I took the mass and I multiplied by the acceleration. Okay? What is this one? Whoa! It's a lightsaber. And I can, wait, what can I do? There's an arrow. I can rotate it. No way.
Innovation 2013.
That's kind of cool. Some nerd thought of that at one point, right? I mean nerd in a good way, obviously. I kind of enjoy that. Anyway, what about the other topic? Gravitational force. Gravitational force. F equals G m1 m2 over r squared. How do we do on that for the homework problems? Gravitational force problems. Fg equals G mm over r squared.
I'm not sure, what does the G mean in that equation?
All right, this capital G is a constant that is used to make sense of the number you're getting. It's a unit, or it's a derived value for the universe. It's an empirical value that people have come up with because of what we experience around us. It's a number that makes it work, to be honest, and it works throughout the galaxy. It's a constant that's a constant of nature, like pi. Like something like Planck's constant you'll learn about is represented by h. Coulomb's constant is lowercase k. They're numbers that exist in nature that occur, and they always obey these laws. They're empirically derived using experiments usually, and then they're proved or backed up theoretically. Okay, so it's just some number, really.
So like,
It's given, sorry.
So
oh, it is, okay.
It's given on the formula sheet at the bottom. I also gave it in the notes.
Okay, so let's do that.
6.67 times 10 to the negative 11. It rhymes if you want to remember that. It's easy to remember.
Oh, should I ask you if it was
Yeah, it's on the bottom of the formula sheet. For problems like these, you should be able to solve for anything. And one of your homework problems asks you to solve for the distance between the two planets. Please, please be careful. Just flip the r squared and the fg over here. Flip them. If you're solving for the distance between the planets, just do this. Okay, you can do that. We did it in the last chapter. We did it in chapter 2. It's the same thing. And then if we want to get r by itself, take the square root of the whole thing. And again, take a look at the g, the capital G. Watch what I'm going to do. Take a look. Oh, so then I'm going to put it in the numerator.
Wait, why?
I can do that. That has no effect on the problem. I can make the numerator, this whole thing up here. I can make my line a little slanted and put the g up top. Because g is a multiplier. It doesn't matter if I put it out in front or at the top. Either way, I'm multiplying it. It's really g over 1. So I'm multiplying it. So if you want to think about the formula this way, instead of in the front, it makes no difference really. Okay? It makes no difference. It's traditionally written the way at the top because you always want to put the constant out front. That's why it's written that way. Scott?
Why did you get FC? Why did you divide it?
If we were solving for the distance between the two objects, and you wanted to solve for r, just flip them. Remember to flip fg and r squared.
That's supposed to be a G, right?
Wait, but that's.
Oh, geez. I'm sorry. Is that what you were saying, Scott?
Yeah.
Sorry. You just did FC a moment ago. FG, yeah. Thank you, Scott. And others.
Wait, what's that C?
In the last example, centripetal force. I
Oh.
was just thinking about that. What else? That was it. I did the ones where what happens if you double the mass and you double the distance between the planets, stuff like that.
The videos are up, right?
Okay, videos are up, yeah. And I'll put the other classes' video up also to see the examples from theirs. I will put the 2 examples that I did this morning in office hours with those who came. I'll put them up online. You'll only be able to look at them. There's no video or anything. It'll just be like a PDF of the example with the worked out solution below it. You can read that if you want for another example to help you. Okay, but there's no video. If you want the video, you come in the morning, I guess. It's not recorded though. Okay? All right, I'm going to give you a little bit of time to work on your problem sets. I don't know how much time is really left right now. If there's much.
5 minutes.